Hello students, hope you all are doing well. Here in this video, we are going to present you, introduce you one subatomic particle. Is the very first subatomic particle that they have revealed. It's the electron. Students, we are going to talk about the discovery of electron in this video. It was after Dalton, as presented in his atomic theory, then people started talking about the smallest, simplest unit of these all the matters. They first believed, according to Dalton, its atoms. These all are made out of atoms. You can't further divide. Those are like golf ball. Therefore, that structure is referred as the golf ball model of Dalton. But later on, it was revealed that subatomic particles are there, making atoms. So, if you already know those subatomic particles, electrons, protons, neutrons, positrons, mesons, and such others as well. So, you have such subatomic particles, they are within atoms. Then students, it's first discovered, revealing that there need to be at least one subatomic particle as electron. It was J.J. Thomson revealed the existence of electrons for very first time. So it was made with experiment series that J.J. Thomson carried out with cathode rays using cathode tube. What are cathode rays and what is the cathode tube? So let's first find it out. What is the cathode tube and what are the cathode rays? Students, in their efforts, those things named as electric conductors and insulators, they listed various things as this is an electric conductor and this is an electric insulator in such a manner. Based on the electric conductance, those fellows started categorizing things they met with as electric conductors, insulators. When they conducted electricity, they named as electric conductors. When they were unable to conduct electricity, named as electric insulators. For an example, a metal took and found out whether it conducts electricity. Yes, it does. So it's an electric conductor. A wood. So then they check whether it conducts electricity. Finding no, it does not. Then they listed it under the category of electric insulator. Glass, insulator. So likewise, they categorize various things they met with, not only solids but also liquids. Finally, they wanted to check whether a gas could conduct electricity. The best and the most common mixture of gases is the air. They wanted to check whether air could conduct electricity or not. So, students, in their very first effort, they realized that no, air does not conduct electricity. So, they named air as an electric insulator. But one scientist did not give it up, checking whether still air could not conduct electricity or not, means could. So, his name was William Crookes. Scientist named William Crookes tried something like this. He prepared a glass tubing. So, there were two electrodes kept, let's say metal rods kept at two sides. And he connected that to a very high voltage supply. Let's say a voltage difference, high voltage. It was a high voltage supply. Then students, it's further, he fixed this tube with a vacuum pump, thinking as to remove some air when it does not support. Means at the very beginning, when it was just left, he did not observe anything. So he wanted to check reducing air there, whether it's still the same. So he reduced amount of gases they are inside. So with that, the pressure inside got reduced. So with the vacuum pump, he reduced the pressure continuously. When he was doing that, he could observe a glow appear there at the side of the negatively charged electrode, what we refer as the cathode. Nearby the cathode, there was a glow appeared, negatively charged. This is positively charged. We call it the anode. So when he was reducing the pressure inside the tube, giving a high voltage, he could observe a glow appear there. When he was further reducing the pressure inside with the vacuum pump, he could see that this shine appeared was traveling there towards the anode, resulting a dark region in between. Then he thought, this dark region here I am having, quite not normal, is having due to the passing of a type of rays. So thinking that to reveal the rays, he placed a screen there. A screen which was fluorescent active. What is fluorescent active? When those rays that you can't see, spot on those make illuminations. So then you could see them. It was a metal sheet coated with zinc sulfide solid, which is a white colored solid. So he coated some zinc sulfide upon the metal sheet and used as a screen. Then he kept it on the path of those at that dark region as to reveal any rays if those are traveling. If any rays are traveling, then those would spot on the screen, giving an illumination. Then you would be able to reveal the rays. Okay, then we could see some yellowish green rays they are evolving. So then he revealed that these kind of rays are evolving from the cathode when you provide the high voltage with a low pressure inside the tube. So for that reason, those were originated or started from the cathode. He named them as the cathode rays. The tube is now called the cathode tube. So it was William Crookes revealed that, invented the cathode tube. Therefore we could call it Crookes tube as well. Okay, then students, that's the story of these cathode rays. It was then after J.J. Thomson worked on these cathode rays as to find out, reveal what truly these cathode rays are. Actually, William Crookes did not further find out what are the constituent either particles or energies that you have within these cathode rays. He revealed the cathode rays, that's only. So it was after him, William Crookes, J.J. Thomson did some experiments to reveal the nature of these cathode rays. He changed the way this cathode tube is for sometimes, as well as the type of the cathode, and he did various different experiments as to reveal the property he wanted to check out. Okay, I'm now going to give you those series of experiments carried out by J.J. Thomson, and the honor of finding out, or let's say discovery of this subatomic particle electron goes to J.J. Thomson. These experiments on cathode rays finally led to discover the subatomic particle. J.J. Thomson through this discovered the very first subatomic particle. It was the electron. Okay, then let's find it out how J.J. Thomson carried out his experiments on these cathode rays as to reveal various properties. Let's find it out. Students, J.J. Thomson first wanted to check whether these cathode rays travel in straight lines or not. Okay, do you know what he did upon that? Students, it's he changed the shape of the cathode tube, and thereafter it was no longer using a vacuum pump, using a low pressure inside. It was a sealed glass tube he was using. So then the cathode was placed there. This is the cathode, negatively charged electrode. This is the high voltage supply. Then he placed the anode somewhere like this. This is the anode. So then on the path of cathode rays, he placed an opaque object. He wanted to check whether the shadow of the object is spotting on the other side, rear side of the opposite side of the cathode. So its students, he coated a very thin smear of zinc sulfide upon the wall opposed to the cathode there. So it was his purpose. If these cathode rays travel not in straight lines like in curvy paths, then it's not a shadow you could observe with fine edges, sharp edges. So anyway, what he finally could observe was the shadow of the object with sharp edges. It was with sharp edges he could observe the shadow of the object. So what's the conclusion that you would make there? If you get such observations, it's for the reason that cathode rays do not penetrate or kind of go in. It's one reason is they do not penetrate the object, and the other reason is they do not go in curvy paths. It's for the reason cathode rays travel in linear paths, straight lines. So the conclusion you could make there as the cathode rays travel in straight lines. Okay students, next he wanted to check whether these cathode rays are carrying a charge or not. Thinking that, he thought if these cathode rays are having a charge, those would respond on an electric field as well as a magnetic field. So when you have cathode rays traveling, when you expose an electric field perpendicular to that, then there would be a response, as there would be a deviation of the cathode rays traveling path, is what he thought. Then he thought if there is no charge, there won't be any deviation of the path. As well as he thought when you expose a magnetic field towards cathode rays, when cathode rays travel, when you expose a magnetic field perpendicular to cathode rays traveling direction, there would be a deviation of the path of those cathode rays if those are charged. Thinking that, he carried out two experiments. So one was exposing a magnetic field towards the cathode rays. The other was exposing an electric field towards the cathode rays. He carried out two experiments. Let's find them out. Let's first talk about the magnetic field thing. Students, he first wanted to have a fine beam of these cathode rays. For the reason, when there is a cathode ray tube like this, having a cathode here the anode, here the cathode. So those could emit cathode rays all around. Therefore, he first blocked all the cathode rays emission towards this direction. So it's then after he made a slit of that metal sheet that he used to block those cathode rays. Then he could resolve a beam of cathode rays. So when there was a screen kept, there was a fine beam of cathode rays could obtain there. Then what he did next was he brought two magnets as to insert a magnetic field perpendicular to these cathode rays traveling direction. So it's S pole and N pole, means south and north. Two poles of magnets were brought as to insert a magnetic field. When you do that, when you insert a magnetic field perpendicular to the cathode rays emitting direction, what would happen? It's the principle of a motor. When you apply Fleming's left-hand rule, when you have current passing in this direction through a conductor, so it is the current direction with your middle finger, and when you have a magnetic field inserted in this direction from north to south, magnetic field with your point finger, your thumb would show you the imbalance force inserting on that conductor wire. So likewise, it's if we analyze these cathode rays, the true nature of the cathode rays are, students, let me reveal this thing. Actually, cathode rays consist of electrons. It's a beam of electrons what you get as the cathode rays here. Then when you call it that cathode rays travel in this direction, it's like a current traveling in the opposite direction. So you have the current direction here, there. Then if you are having the magnetic field inserted in this direction, there would be downward force. So students, as it was expected, those cathode rays deviated its path, bending downward. That one, the observation was made there. Okay, again the experiment was when those cathode rays, a beam of cathode rays, is exposed to a magnetic field, perpendicular magnetic field, those cathode rays deviated their path and traveled, deviating perpendicularly to the magnetic field, traveled in the direction where a negatively charged rays would travel. Therefore, he concluded, J.J. Thomson concluded with that cathode rays are negatively charged. Hope you could understand. So, students, in this next experiment, what he did was, it was the same setup, but now not magnets. It was, he introduced an external electric field. So, it was an external electric field introduced on the cathode rays. So, as let's show it, here the positive end, here the negative end of external electric field. When there was an external electric field introduced, those cathode rays deviated, bending towards the positive end of the external electric field. That also proved the cathode rays are negatively charged. Okay, so far we have revealed cathode rays travel in straight lines. Those have have a negative charge. Those are negatively charged. Then students, what he got in his mind next was to check whether this cathode ray consists of particles or not. Whether these cathode rays could insert an imbalance force on an object or something or not. So, whether these cathode rays are having particles with a momentum or not. He simply wanted to check whether these consist of particles. So, what he did next was something like this. Students, it's Thomson held a paddle wheel. They are inside of a cathode tube that could roll upon two supporters kept inside the tube. It was a paddle wheel kept inside a cathode tube. In his next experiment, Thomson designed it like that. So there were two electrodes, means one was the anode, other was the cathode. In a way like this. So for this time, not naming straightly it as cathode or anode, I will give it in this manner. This is the positive end. This is the negative end. So, once I could make this into the cathode and this into the anode, means this into the cathode once and this into the anode. This is a bridge key. It is a bridge key. Bridge key. Bridge key could, when you once switch it in one direction, one would be the negatively charged, other would be the positively charged. One would be the cathode, other would be the anode. And at the other time, when you switch it other way, then this would become the anode, this would become the cathode. That is the way the bridge key works. Then students, there was a bridge key kept. So, then there was a paddle wheel held there inside the cathode ray tube upon two supporters as it could roll through it. It's a light paddle wheel, and on each paddle those fluorescent active substance, zinc sulfide, was spotted. So when once it was switched on, spotting those cathode rays on paddles, those that paddle wheel start rolling towards the anode and stop there at the anode end. Then students, next, when he switched it other way, when this became the new cathode and this became the new anode, again the paddle will start rolling towards the new anode and stop there close by the anode. That's what he made as the observation. So explaining, analyzing those observations, what Thomson told was to insert or to roll that paddle wheel, you need to be able to insert an imbalance force with cathode rays upon the paddle wheel. So, to insert an imbalance force, according to Newton's second law, you need to give a momentum difference. So, when there is a momentum difference, only there would be an imbalance force applied. So by those cathode rays, it's a momentum change giving. So then these cathode rays are having a momentum. So students, to have momentum, those cathode rays needs to be particle with a mass and velocity v. So then these cathode rays are nothing else but particles, consist of particles with a mass and velocity. It was proven that cathode rays consist of particles with a mass as well as velocity. So particle nature of these cathode rays were revealed by J.J. Thomson with that experiment. Hope it's clear. Okay. So the paddle wheel, to move the paddle wheel, they are spotting, after spotting on spotting of those cathode rays on paddles. Those cathode rays need to be able to insert an imbalance force. To insert an imbalance force, those cathode rays need to have particles having a mass and velocity, means the cathode rays need to have a momentum. So then with that, he revealed that cathode rays consist of particles. Okay. Next, students, he wanted to check how these cathode rays get emitted compared to its surface, means emitting surface. So on that, he did something like this. He kept a screen inside, and once there was a convex cathode kept. It is the cathode, convex cathode. So in another cathode ray tube, there was another screen kept. So it was a concave cathode kept. This is the cathode. It is now the shape of the cathode concave. It was a concave cathode. So, placing a screen inside, when it was switched on, he could observe that when there was a convex cathode, those cathode rays were converging, diverging. When there was a convex cathode, those cathode rays were diverging, dispersing all around, not converging. So when there was a concave cathode, those cathode rays were converging, focusing to a center. Okay, so he made those observations. Then he came to the conclusion that to do such, those cathode rays need to get emitted all the times being perpendicular to the emitting surface. Otherwise, those won't behave like. Means when you have a convex cathode kept, those are diverging for the reason those get emitted perpendicular to emitting surface. Then those are converged when you have a concave cathode, again for the reason those get emitted perpendicular to emitting surface. So it's another property regarding cathode rays we could reveal that cathode rays get emitted perpendicular to emitting surface. Then students, it's further, he did something like this. Removing the screen here, he placed a bulb of a thermometer at the focus point and realized that when you switch that on, the thermometer's reading gets increased, means the temperature goes up. So he concluded that cathode rays could result a heat energy. So it could result a heat energy. Then the properties he revealed regarding cathode rays were those cathode rays travel in straight lines, carry a negative charge, consist of particles with a mass as well as speed, velocity, then get emitted perpendicular to emitting surface and could result an act of heat. Okay. Then students, it's further, he checked something like he wanted to check the E over M, charge over mass ratio. He designed something like this. He placed a cathode there inside a cathode tube. It is the cathode, and for this time it was a metal sheet kept as the anode. There was a slit hole at the very middle of the metal sheet, means the anode. this is the anode. So then those cathode rays which came straight to the slit traveled in a direction like this. Then students, there was an external electric field inserted. So then he checked for the deviation, the angle, degree of deviation, angle. So he told this deviation of the rays would be dependent on charge. If you have a greater charge, the attraction inserted by this would be greater. Therefore, the deviation, therefore the degree of deviation, the angle would be higher, greater. So then it is charge. So this deviation exhibited is directly proportional. The response means the deviation is directly proportional to the charge. If you have a high charge, greater charge, the deviation would be more. Then further, if it is a lighter particle, then also you could easily change its path, deviate more. Deviation would be more if the mass is less. If the mass is high, the deviation would be less. So then the deviation would be inversely proportional to the mass. So observing the deviation, he told that deviation depends on the charge over mass ratio. Charge over mass ratio. So he gave a value upon charge over mass ratio for those cathode rays. He calculated this, knowing the provided electric field. He knew what's the electric field. Therefore, based on the deviation, he gave a value standing for the charge. Charge is E, mass is M. Charge over mass ratio, he calculated a value. So students, the value he got at the very first time was 1.759 into 10 to the power 11 coulombs per kilogram was the value he obtained. Then he changed the gas kept inside the cathode tube and checked again whether this value will get changed based on the gas inside the cathode tube. No, it didn't. So whatever the gas is kept inside the cathode tube, the mass over charge ratio of those cathode ray particles would be the same. Then he changed the metal, type of the metal of cathode as well as anode and checked for whether there is any change of charge over mass ratio. Still it was the same. Then he realized, students, the charge over mass ratio is same for the reason all the cathode ray particles are identical, are the same. So now he was at a position like then this seems like within an atom you have another particle, you have one particle which is smaller than of atoms. These particles are identical in every aspect. These are negatively charged. Then students, he wanted to name these particles. So earlier, before J.J. Thomson, there was a scientist named G.J. Stoney. He has proposed an idea that in electricity there would be a smallest unit, smallest amount. He named that amount, he named that smallest unit of electricity as an electron. So then Thomson, seeing it's quite similar to that idea of G.J. Stoney's electron, he named this particle newly revealed as electron. That's the story of electron. That's the discovery of electron. Students revealing the properties of those cathode rays as travel in straight line, consist of particles with a mass and velocity, negatively charged, yet emit perpendicular to emitting surface, as well as could result an act of heat. So he, J.J. Thomson, revealed that there would be a particle within an atom which is negatively charged, having E over m ratio like this. So he named that as the electron. When you honor the person who discovered the electron, you need to honor J.J. Thomson. But if it is about who named this electron or who gave the name of electron, it goes to G.J. Stoney. It was his idea. Then students later on, a scientist named Mulliken, or we would call him Millikan as well, in his oil droplet experiment revealed that the charge of an electron would have the size of 1.602 into 10 to the power minus 19 coulombs. Mulliken revealed the charge of an electron being 1.602 into 10 to the power minus 19 coulombs. Then after having that, substituting the charge here, it is the electron's charge over mass ratio is 1.759 into 10 to the power 11. 759 into 10 to the power 11 coulombs to kilogram. So it's substituting the charge here, this charge here, it's you would get the mass of an electron being what? It is 9.107 into 10 to the power minus 31 kilogram. Okay, those are the information things regarding electrons. So students, so far we have found out how the subatomic particle electron was discovered. In our next our next video, we are going to consider the discovery of proton. So hope these things are very simple and clear. If you have any doubt, any problem, any idea, we value those. So you mention those there in the comment box. Students, we are going to round up here in this video with the hope to meet you in our next video. Okay, goodbye.